Okay,
there we go.
whatever.
We're good.
All right, great. So hi everyone, thanks so much for having me. I'm really excited to be here. My name is Farnik Nikakhtar. I'm a PhD student at UPenn in Philadelphia. And today I'm gonna talk about the star populations in the solar neighborhood by using both observed and simulated catalogs. This is a paper in collaboration with these great people, and we have used Gaia-APOGEE. So in this meeting, I'm so excited to learn more about and better understand the Gaia data. And so the simulations we have used is Fire 2 simulations. Of course, simulations are not exactly the same as the Milky Way, but we have used them to better understand our real data and better understand different scenarios, or in general, questions we should be asking of our real data. So let's just start from this Toomre diagram that we have seen several times in the previous talks very well. It basically motivates the decomposition of the solar neighborhood into some, components with some hard cutoffs that we can see. So our main question in this work was that what does the data tell us directly about the number of distinct populations if we don't want to have these hard cutoff, for example, for having the halo, thick disk, or thin disk. So to test this idea, we took the agnostic approach of allowing the data itself to tell us what the distribution looks like. We constructed a Gaussian mixture model for both simulated and observed data using measured velocities in this space, actually Vxc and Vy, and iron abundances, Fe over H, as the distributions to be decomposed. So before starting to talk about this GMM model, we need to know, I think, a few points about the simulations. And so the first thing is that we have 3 simulations. They're actually Ananke mocks, which are Gaia-like synthetic surveys. We have M12F, M12I, M12M, and we have 3 of them, and in each of them we have 3 different solar positions. So technically we have 9 simulations or 9 different solar neighborhoods. And in fire simulations, there are 11 elements, these elements tracked with 3 sources of chemical enrichment, which is type 1 supernovae, type 2, and winds. So for our paper, actually, we've generated or implemented the apogee error models for these 8 elements on top of the surveys. And actually, our Gaia-APOGEE mock catalogs, which are based on the fire simulations, will be publicly available as a value-added catalog to SDSS DR data release 17, I think, in a few months. And the second point about the simulations is about the definition of the solar neighborhood. To define the solar neighborhood exactly, we do not apply any distance cut, but about the quality cuts on parallax, metallicity, and radial velocity that we have in the mocks give us a radial coverage around 4 to 12 kiloparsec in galactocentric distance, which is similar to the coverage we obtain in the real data catalog after applying all the quality cuts. So, okay, for the Gaussian mixture model, we want to make this model, our model in this space, all the velocities Vx, Vy, Vz plus Fe over H. And we should know that we want to actually use the Cartesian coordinates, not the cylindrical. We want to use Vx, Vy, Vz for the 3D velocities that we have to avoid imprinting assumptions about symmetries, right? So in this model, we have parameters. It's a summation over different Gaussian distributions. So we need to set the number of components for this model. We have mean vectors for each component and covariance matrices for each component, and weights for each of these Gaussian distributions. So as Emily asked Drake about this question about the optimal number of clusters, and when we want to use generally these types of unsupervised learning or clustering algorithm, like k-means or Gaussian mixture models, we need to fix the number of components first. So we need to have a measure to find the optimal number of clusters or the best number of clusters that we have, that we can find in the data. For that, we want to use Bayesian information criterion, or BIC. It has two parts. One is it's related to the penalty for adding more components, and the other part, the second part of this is likelihood of the best fit model with k parameters. So this k is the number of free parameters that we have in our model. NC is the number of components, and F is the number of features that we have, which is 4 here. So when we measure this BIC for all these 9 different simulations, 9 different solar neighborhood that we have, we can see there is a clear improvement up to 5 components, and nearly no appreciable improvement after that, which is called, elbow rule in these BICs. And we want to select 5 because 5 components is the best number of components in this clustering in our data or in our mock catalogs. Because actually, on top of these elbow rules, the next components, like 6 components or more, they do not correspond to a distinct group, and they just split one of the pre-specified clusters that we have seen. So it's interesting that we have 5 number of components. I think in several papers, and also Sven mentioned yesterday in his talk that these 5-6 components are interesting number when we use these clustering algorithm for Milky Way data. So perfect. This is if you look at these 5 components in this augmented Toomre diagram, which is FV VXZ, FE over H, VY. We see, in these components, two of them analogous to the thin disk. We have a thin disk here, and the metal poor halo, right? But instead of a single counterpart to the thick disk, there are 3 intermediate components which have some overlap in this region. This panel here, it shows the distribution of probabilities of belonging to each component for the different stars in our samples. Perfect. So by looking at the series of distributions of different stellar properties for each component in these mock catalogs, we can see these different components actually have, for example, distinct age or alpha distribution and formation histories. This is the formation distance that we have. Even though, these data, these features are not used to fit the model. We just used X, VY, VZ plus FE and H to fit our data. So it says that they might have, all right, they might have, all right, so I should go fast. Okay, so, even here in alpha age distribution, we can see that these distributions are different. So we can follow all these components in different simulations to find the history of each of them. As Emily showed, these plots, formation distance versus age, we can see different patterns like late accretion or radial mixing here. And so we can see these patterns that, in addition to these plots, from these plots, we can also look at the movies that we have from this simulation to find these different scenarios for the origin of these different components. So we can see, for example, the oldest stars are from this halo-like component, and we have some mergers. All the stars in these components, they usually form in a very small radius. And these percentage are the weights of each component. And as it goes on, we can see we have more components in the thin disk, at the late time. So for the real data, we work, it's interesting that we did the same analysis, and we find that in the Gaia DR2 apogee DR16, in the real data, the optimal number of clusters is again 5. So the distributions, of course, they are different, but we still have a obvious halo and the thin disk component, 3 intermediate components in this Toomre diagram. These are the same plots for different distributions, and this is a table that shows our models that we can, anyone can quickly implement it to classify the stars themselves by just, finding the probabilities of belonging to any of these 5 components. So yeah, these are important. The weights are important. So the final scenarios that we can say that, for example, 4% of the data is from the halo component, 46% is from the thin disk component, 22% is the most metal-rich thick disk-like component, and 27% are from the two top 2 thick disk-like components. And so, yeah, there are more details and discussions about these different scenarios in the paper. I just mentioned a brief summary of them. And so if you're interested, this is the archive number, and also I'll be happy to talk more over the Slack right now. Yeah, thank you so much.
Hey, thank you so much, Farnik. Are there any questions for Farnik? I have a question. I'm getting to ask all my questions. So I'm curious how you interpret the fact that there are 2 clusters that are related to, like, why there's so many components that are related to the thick disk, essentially.
Yeah, actually, let me share my screen again. Sorry. Yeah, we can see, for example, for these 3 intermediate components, these are for the real data that we have. In a X, Y, Z plane and velocities, we can see one of them, has negative VZ velocities, and the other one has positive. So basically, we have one of them is the most metal-rich thick disk-like, and which is related to the stars that have been heated by accretion. And the 2 other components that we see, they are thick disk-like. They are, they compromise the velocity asymmetric because of these, VZ, VX, VY, VZ plots that we have, and also alpha enhanced thick disk that we see in the real data, actually, I think.
Very cool. Very cool. Thank you. Sven.
Sure.
Thanks. Yeah, great talk, Farnik. I was wondering, when it comes to these Gaussian mixture models, they of course try to find something that they can describe in a Gaussian way, right? So when it comes to this 4% halo component, I guess that's the least Gaussian-like in the velocity space. How many components would you actually have to allow to fit so that you could find also substructure there? I know the BIC doesn't suggest it, but we know that there is like the Gaia sausage Enceladus. Right. Have you been able to somehow find one of the components that would just describe that one?
Well, actually, because there is one point about the volume that we are using. So we're using actually our data, it's very close to solar neighborhood. That's one point actually that maybe have this problem about the 4% of the the halo component, but not about the Gaia Enceladus, but for moving groups that we have. For example, when we plot this is a heat map plot of the Vy Vx, for example. When we make the residual plot of our Gaussian mixture model versus the kernel density estimate that we have from the real data, we can see that the overestimated and underestimated regions are exactly at the same point of these moving groups. But yeah, I'm not sure about the substructures like Gaia Enceladus or
Yeah, yeah. So most likely, if you would add one more component, the first thing that would be resolved would be like Hercules instead of Gaia Enceladus, if at all, right?
Yeah, yeah,
Yeah, would be interesting to see. Yeah. All right. Thanks.
yeah, sure, sure.